This is going to be a really quick rundown of our intermolecular force unit notes, essentially what you need to know for the test. Because of that, everything's already written out, and I'm just going to go through and review it. So remember that our intermolecular force is really our attraction between molecules. So the force that we're talking about is attraction, and it's the attraction between molecules. There are three things that go into determining different properties. We use our intermolecular force to determine properties, but there are some things that go into it first. The first thing you need to consider, step one, is you need to consider bond polarity. Bond polarity is it can be ionic or covalent, and our covalent breaks into polar and nonpolar. And we determine these by the electronegativity, which is written in orange. Once we determine the bond polarity, then we use that for step two to determine the molecular polarity. So molecular polarity, if the molecule is nonpolar only if all nonpolar bonds in our molecule, or if there are polar bonds, but it's symmetrical. So for example, if I have carbon tetrahydride, that carbon and that hydrogen is an electronegativity difference of 0.35. So it consists of only nonpolar bonds, so my molecule is nonpolar. If there are polar bonds, so for example, in my carbon dioxide, this is a polar bond towards the oxygen. Don't forget your dipole moments and your dipoles. A lot of you have been forgetting those, and those are easy points to lose on a test. And so with our dipoles we see that I have negative charges pointing out from the carbon. And so those are polar molecules. It's polar, but does it have any lone pairs? No. Is it surrounded? Is the central atom surrounded by only one type of atom? Yes. And so because of that, that makes it symmetrical. That means it's nonpolar. And what symmetrical means is that these dipoles are like vectors. So here was my one dipole, here was my other dipole. Since they're like vectors, because they're equal, their change is 0.89. I have 0.89 pulling to the left oxygen and 0.89 pointing to the right oxygen. So because of that, they cancel out. And so that means the overall force is 0, meaning this is a nonpolar molecule. And that's where we get that from. It's a polar molecule if it has polar bonds and it's not symmetrical. So for example, my oxygen, my water, has two lone pairs. Remember, those two lone pairs have more force on the bonded pairs. And so they force these bonded pairs to be directed down. And so I have polar bonds, and it's because of these lone pairs pushing those bonds down, they're going to cause vectors that won't cancel out. This vector is essentially composed of two vectors, and we're going to keep it very simple. We're not going to worry about the quantities of the vectors. That's not what we're focused on. This is just a quick and dirty trying to make sense of things. And so if I take my vectors and I break them into their two components, the x component and the y component. Well, when I look at this, my x components are going to cancel out because they're in the same direction. My y components, however, are both pointed in the same direction, and so it's not going to cancel out. And so what we say is that we have a polar molecule, and the molecule itself has an overall molecular polarity, a molecular dipole. And so my molecular polarity is pointing in the direction of where my electrons are hanging out at. And since my vectors of my electrons are pointing up, that means my overall molecular polarity is up. This is also why if I have something different surrounding it, so let's say I have carbon and chlorine. Oops. And oxygen. And so, like I said, I know that this is a change of 0.89. I didn't calculate the other one ahead of time because I just kind of threw this in off the top of my head. So let me calculate it real quick. That's not going to work. Oh, wait, it is. I did the wrong number. Sorry for the delay there. So this is 0.61. And so, because my vectors are going to have different amounts of pool, that means that my vectors can't cancel out. Even if they were in a linear shape, they can't cancel out. So for example, with this, when I had my oxygen, and then let's say I have it double bonded to a sulfur, this would still be a polar molecule because the difference here is 0.97, whereas my difference here was 0.89. Now they're close, but one vector is larger than the other, and so they're not going to completely cancel out. It will have an overall directional molecular polarity towards the sulfur. Oops, towards the sulfur. That should be a minus. So hopefully that helps that to make more sense. Finally, once you determine if your molecule is polar, then depending on the strength of that attraction between molecules, that's what determines the intermolecular force. That's the amount of polarity or the amount of strength in your bonds causing the molecule to be polar determines how tightly they're held together towards its other molecules. So nonpolars have a very, very weak attraction. Almost non-existent. It is a little bit there. They're not repelling each other, but they're very, very, very weakly attracted. Polar molecules have a moderate attraction. It's not nearly as strong as our ionic. Our ionic is our strongest, but because it has those partial negatives and partial positives, the partial positives of one molecule will be attracted to the partial negative of the other molecule. And so they are held together a little bit more tightly than our nonpolar, but not as much as our ionic. And so by looking at these, now we can talk about the properties. So for example, if I want to look at boiling point, well, my boiling point is going to be in order of how strong the attraction is between my molecules. So in this case, my nonpolar, since it has very weak attractions, is going to have a very low boiling point. My polar molecules are going to have a moderate boiling point, and my ionic will have a very high boiling point. And so if I had to rank these, I would rank nonpolar as the least, then polar, then ionic. Hopefully that helps you to understand these intermolecular force notes a little bit better. Have a great day.